You ever wondered about the exact moment the world switched on? For most of human history, night meant darkness, lit only by candles or gas lamps. Electricity was nothing more than a laboratory curiosity, a spark in a bottle. But in the 19th century, a series of mind boggling breakthroughs changed everything, shifting humanity from the age of steam to the age of light. It all started in 1831 with an English scientist named Michael Faraday. He discovered something called electromagnetic induction, the simple but revolutionary idea that moving a copper wire through a magnetic field forces an electric current to flow. Faraday built a crude spinning copper disc between two magnets. It didn't power a city, but it proved the big concept. You could convert mechanical motion into pure electrical energy. And it took another 50 years for anyone to scale this up for the public. The real turning point came in 1882, a legendary year for energy. In London, Thomas Edison built the world's first coal-fired power station. A few months later, in September, he switched on the famous Pearl Street station in Lower Manhattan. Using massive steam engines to spin heavy copper dynamos, Edison safely sent a 110 volts of direct current through underground cables to light up local buildings, including the offices of the New York Times. Just weeks after that, a plant in Wisconsin used a river water wheel to create the world's first hydroelectric power. The basic loop they used is the same one we use today. Burn fuel or use rushing water to spin a turbine, spin magnets past copper coils, and push those moving electrons out into a grid. Those early systems used direct current, or DC, which couldn't travel more than a mile without losing power. Within a decade, pioneers like Nikola Tesla and George Westinghouse introduced alternating current, allowing electricity to travel hundreds of miles efficiently. But the spark that lit the modern world truly caught fire in 1882, forever changing how we live, work, and see the dark. For more information, visit www.globalpowernews.com. Follow the YouTube channel, Anawas Laco Power Pro. If you like it, share it with others. Imagine stepping back into the year 1883. If you wanted to light a room with electricity, you had to live within a strict 1 mile radius of a generating station. Back then, Thomas Edison's direct current system ruled the day. But DC had a fatal flaw. It couldn't travel. Power dropped off so fast that sending electricity across a city was physically impossible. Generating plants were tiny, localized, and driven by massive clanking steam pistons that shook the ground with every stroke. Electricity was a localized luxury. But over the next 42 years, the world witnessed an industrial transformation unlike anything before or since. The spark that changed everything came in the late 1880s, when George Westinghouse and Nikola Tesla could step voltage up to staggering highs, shoot it across hundreds of miles with almost no energy loss, and step it safely back down for the consumer. The climax of this war of the currents came in 1895 at Niagara Falls. When the switches flipped on Tesla's massive AC generators, they successfully sent power 22 miles away to Buffalo, New York. For the first time, humanity decoupled power generation from the immediate vicinity of its users. But as the electrical systems grew, the old mechanical engines began to literally split at the seams. Those giant reciprocating steam pistons had a strict speed limit. If you ran them too fast, the vibrations would tear the machine apart. Enter Charles Parsons. In 1884, he invented the multi-stage axial steam turbine. Instead of pushing a piston back and forth, high-pressure steam blew directly through rows of curved blades, spinning a central shaft continuously. It was smooth, it was incredibly fast, and it changed the economics of power forever. A turbine took up less than a quarter of the space of a piston engine, yet by 1925, a single turbo generator could pump out over 100 megawatts of power, enough to light entire cities. To feed these monsters, fuel usage had to evolve too. In the 1880s, teams of workers manually shoveled lump coal into low-pressure boilers, wasting over 95% of the fuel's potential energy. By the 1920s, automation took over. Power plants began crushing coal into a fine microscopic powder, blowing it into furnaces where it combusted instantly in midair. Along with the discovery of massive oil reserves, these advancements pushed thermal efficiency from a miserable 3% up toward 20%. By 1925, the isolated dynamos of the past were gone, replaced by interconnected high voltage grids operating at up to 220,000 volts. In just 42 years, the vision of Tesla, Westinghouse, and Parsons had scaled up to become the literal lifeblood of modern civilization. For more information, visit globalpowernews.com or my YouTube channel, Nawaz Laco Power Pro. Don't forget to like and share. Imagine a world where electricity was a luxury, localized, fragile, and bound to the limits of raw coal. In 1925, the average power plant was a noisy, inefficient beast. Steam pressures rarely topped 30 bar, and efficiencies hovered at a measly 15%. If you wanted power, you had to live right next to the plant. But over the next 50 years, a quiet revolution of steel, science, and fire would rewrite the rules of human civilization. First came the shift in how we burned. Engineers traded heavy grades for pulverized coal, blowing combustible dust directly into massive boilers. Then they targeted the laws of thermodynamics by pushing steam pressures past the critical threshold of 2001.1 bar. Plants like Ohio's Philo Station in 1957 bypassed boiling altogether. They conquered supercritical steam, driving efficiencies past 35% and paving the way for gigawatt-scale giants. But the mid-century brought a completely new force to the grid. In 1954, Soviet scientists plugged the world's first nuclear reactor into a public grid. Within 3 years, America's shipping port station proved that pressurized water reactors could safely power entire cities. The atomic age had arrived, promising massive carbon-free baseload power that would fuel the post-war industrial boom. Massive power meant nothing without a way to move it. Local grids began to merge, forming regional supergrids. Transmission lines vaulted from double-digit kilovolts to towering extra-high voltage AC lines operating at over 700 kilovolts. And in 1954, high-voltage direct current, or HVDC, emerged, enabling utilities to send bulk power across vast oceans and connect entirely independent grids. By 1975, the local powerhouse of the 20s had evolved into a massive interconnected gigawatt-scale engine. We had tamed steam, conquered the atom, and wired the globe. But as a global energy crisis loomed in 1973, a new challenger was waiting in the wings, one that would redefine efficiency forever. Next time, we step inside the rapid-fire evolution of the modern gas turbine. For more information, visit globalpowernews.com or find my YouTube channel at Nawaz Laco Power Pro. Don't forget to like and share. By 1975, humanity had built an industrial empire on the back of massive centralized electricity grids. We had tamed supercritical steam, unlocked the power of the atom, and wired the globe with towering extra high voltage lines. But the foundations were shaking. The 1973 oil crisis exposed a brutal reality. The global power engine was deeply vulnerable, rigid, and heavily reliant on fossil fuel baseload plants operating at thermal efficiencies that rarely crossed 35%. As the world entered the final quarter of the 20th century, a new era of engineering was born. Over the next 50 years, the grid would undergo a radical transformation, evolving from a rigid analog machine into a dynamic, intelligent, and decarbonizing ecosystem. This is the story of how we powered the modern world between 1975 and 2025. The first major breakthrough of this new era did not happen in a laboratory. It happened inside the combustion chamber. Desperate for fuel flexibility and rapid deployment, the power industry turned to heavy-duty industrial gas turbines, borrowing advanced metallurgy and cooling techniques from aerospace engineering. Engineers pushed turbine inlet temperatures past 1500 degrees Celsius, using single crystal superalloys and specialized thermal barrier coatings to survive environments hotter than the melting point of the metal itself. But the true game changer was the commercialization of the combined cycle gas turbine, or CCGT, in the 1980s and 90s. By capturing the blistering exhaust heat from a gas turbine and routing it into a secondary steam turbine, engineers did the unthinkable. They shattered the long-standing thermodynamic glass ceiling, driving plant efficiencies from 35% straight up to an astonishing 60% and eventually breaching 64% by the 2020s. While gas turbines were rewriting efficiency records, the nuclear sector was facing a profound crisis of confidence. High-profile accidents at 3 Mile Island in 1979 and Chernobyl in 1986 forced a massive regulatory and philosophical shift. The industry had to pivot from raw scaling to absolute inherent safety. Enter Generation 3 and 3 Plus designs. Engineers pioneered passive safety systems that eliminated the need for human intervention or emergency electrical backup power during a crisis. Instead, these systems relied entirely on the unshakable laws of physics, using gravity, natural convection, and compressed gases to safely cool a reactor core in an emergency. By the early 2020s, the nuclear frontier shifted again with the rise of small modular reactors, or SMRs. These factory fabricated flexible units meant nuclear power could finally move away from multi-billion-dollar mega projects and step into the modern world as an agile partner for local grids. While traditional plants were optimizing, a quiet revolution was gathering strength on the margins of the grid. In 1975, solar panels and wind turbines were dismissed as niche experimental novelties. By 2025, they had become the cheapest source of new bulk electricity on Earth. Wind power scaled up at a breathtaking pace. The modest sub-100 kilowatt onshore wind turbines of the 1980s evolved into towering offshore giants exceeding 15 megawatts, with rotor diameters wider than the wingspan of multiple jumbo jets. Simultaneously, solar photovoltaics underwent a manufacturing scale-up of historic proportions. Advanced materials science drove traditional silicon cells out of the lab and into the mainstream, introducing high-efficiency PERC technology, bifacial panels, and tandem perovskite layers. Commercial panel efficiency skyrocketed, while the cost of solar power plummeted by over 90% in just a single decade. But generating this immense volume of clean, weather-dependent power created a massive problem. How do you balance a grid when the sun goes down and the wind stops blowing? The old unidirectional grid of 1975, where power simply flowed from one big plant to a passive consumer, could not survive the 21st century. The transmission network had to become smart. High voltage direct current, or HVDC, became the superhighways of the global grid. Equipped with advanced voltage source converters and modern power electronics, HVDC lines began moving massive blocks of power across thousands of kilometers and under vast oceans with minimal losses. At the local level, the grid was injected with digital intelligence. Armed with phasor measurement units, real-time SCADA systems, and massive utility-scale battery energy storage systems, grid operators began doing what was once considered impossible: balancing volatile renewable energy inputs second by second, ensuring grid stability across entire continents. In the 50 years between 1975 and 2025, humanity did not just build more power plants. We fundamentally re-engineered the lifeblood of modern civilization. We moved from an era of raw combustion and isolated rigid systems into an interconnected, highly digitized, and rapidly decarbonizing global matrix. The 50-year fuse that was lit in the mid-20th century has culminated in the most complex, intelligent machine ever built by human hands, the modern power grid. And as we look to the future, the journey toward a fully sustainable, electrified world has only just begun. For more information, visit www.globalpowernews.com or my YouTube channel at Nawas Laco Power Pro. Do not forget to subscribe, like, and share. From the monolithic, fossil-heavy grids of 1983 to the smart, decentralized energy networks of 2025, humanity's relationship with power has undergone a quiet revolution. For most of modern history, energy meant scarcity, scarce fuel, scarce transmission capacity, scarce resilience, and scarce access. The grid was built around giant plants, long wires, and one-way delivery. But today, Solar fields, battery farms, digital controls, and millions of connected devices are turning that old model inside out. Power is no longer only generated in distant industrial zones, it is being stored, routed, predicted, and optimized in real time. But what lies ahead? Together, we have mapped the past. Now, let us look to the future. Over the next 50 years, we are not just transitioning our energy sources, we are mastering abundance. This is the story of the next half century of power, as predicted by the world's leading engineers, scientists, and developers. Our journey begins with the immediate reconstruction of the grid itself. Between 2025 and 2040, the most important breakthroughs are not only about generating more electricity, they are about storing it longer, moving it farther, and controlling it with far greater precision. Early lithium batteries made the renewable age possible, but they were only the beginning. The next generation brings solid-state sodium-ion batteries, safer chemistries, lower material pressure, and longer useful life. Alongside them, long-duration iron, air, and flow batteries become the heavy foundations of renewable stability. They charge when the wind is strong and the sun is high, then release energy for days when the weather turns. At the same time, the transmission system is rebuilt for a continental and ocean-spanning age. Ultra-high voltage, direct current corridors connect deserts, coasts, offshore wind zones, and industrial centers. High-temperature superconducting cable systems reduce losses so dramatically that distance begins to matter less. Electricity can travel thousands of miles with extraordinary efficiency, turning the planet's best renewable zones into shared global assets. By 2040, the grid is no longer a fragile machine. It becomes an intelligent energy nervous system. By the mid-2040s, humanity steps beyond intermittent harvesting and enters a new nuclear dawn. The old image of nuclear power was defined by enormous custom projects, long construction delays, and political uncertainty. The next era looks very different. Factory-built small modular reactors, or SMRs, are designed to be repeatable, compact, and easier to deploy near the communities and industries that need firm, clean power. Some advanced designs use upcycled nuclear waste as fuel, reducing legacy stockpiles while producing reliable heat and electricity. These reactors do not replace renewables, they strengthen them. They provide a steady baseload foundation that keeps hospitals, data centers, factories, desalination plants, and dense cities running through every season. Then comes the breakthrough that engineers pursued for generations: commercial fusion. Inside magnetic confinement chambers, deuterium-tritium plasma is sustained at temperatures many times hotter than the core of the sun. The plasma never touches the walls. It is shaped, compressed, and controlled by powerful magnetic fields. When fusion finally feeds electricity into the global grid, the psychology of energy changes. Fuel becomes abundant, carbon emissions fall faster. Nations begin planning not around shortage, but around what civilization can build when clean baseload power is always available. As we approach 2075, the energy system expands beyond the atmosphere. Space-based solar power becomes one of the great infrastructure projects of the century. In geostationary orbit, autonomous construction fleets assemble enormous golden collector satellites, kilometers wide, positioned where sunlight is almost constant. Unlike ground solar, these platforms do not face night, clouds, dust storms, or seasonal darkness. They harvest unfiltered solar energy 24 hours a day, then transmit it safely back to Earth through targeted microwave links received by vast antenna fields. On the surface, the grid itself becomes planetary. Artificial intelligence forecasts demand before it appears, balancing weather, industry, transport, storage, and orbital power in one coordinated system. Quantum-secured communications protect the network, while advanced sensors detect instability before humans would ever see it. Electricity moves through a unified architecture that is fast, adaptive, and deeply resilient. The result is more than cheaper power. It is a new operating system for civilization. Remote regions gain reliable access. Megacities breathe cleaner air. Water can be desalinated at scale. heavy industry can run without fossil combustion. By 2075, energy scarcity is no longer the central limit on human progress. The question becomes how wisely we use abundance. We are on the cusp of becoming a Type 1 civilization, capable of harnessing the full energetic potential of our planet and reaching beyond it. That future will not arrive automatically. It will require engineering discipline, public trust, smart regulation, resilient supply chains, and leaders who understand that energy is the foundation of security, prosperity, and human possibility. But the direction is clear. The future of power is bright, clean, intelligent, and limitless. Thank you for exploring this journey with me. Make sure to stay informed as the future unfolds. For more information, visit globalpowernews.com. Subscribe to my YouTube channel at Nawazlako Power Pro. And do not forget to like and share. Imagine holding the power of a star inside a machine here on Earth. That is the basic dream behind fusion energy. In the sun, gravity squeezes hydrogen until atomic nuclei combine and release enormous energy. A fusion power plant tries to recreate that process in a controlled reactor, not with gravity, but with heat, plasma physics, and magnetic fields. The fuel becomes an ultra-hot plasma where electrons are stripped away from nuclei and the gas behaves like a glowing electrically charged fluid. The real challenge is not just making fusion happen for an instant. The challenge is guiding that plasma, capturing the energy it releases, and turning that energy into useful electricity for homes, cities, factories, and the grid. In this video, we will follow the full path from star-like plasma to fusion reactions to heat, steam, turbines, generators, and finally clean electric power. At the heart of many fusion reactor designs is a device called a tokamak. It looks like a giant donut-shaped chamber built to hold plasma without letting it touch the walls. The common fuel mixture is deuterium and tritium, two heavy forms of hydrogen. To make them fuse, the fuel must be heated to temperatures far beyond the center of the sun, often above 150 million degrees Celsius. At that temperature, matter becomes plasma. The nuclei are positively charged, and because charged particles respond to magnetic fields, powerful superconducting magnets can shape and confine the plasma. These magnets create invisible highways that guide the particles around the chamber. That magnetic cage is essential because no solid material could survive direct contact with plasma that hot. Instead of holding the plasma with a physical container, the reactor holds it with carefully controlled fields. Now let's zoom down to the atomic scale. In a deuterium-tritium fusion reaction, two hydrogen isotopes collide with enough energy to overcome their natural electric repulsion. When they fuse, they form a helium nucleus and release a high-energy neutron. This is the key energy carrier in many fusion power plant concepts. The helium nucleus is charged, so magnetic fields can keep it inside the plasma, where it helps maintain heat, but the neutron has no electric charge. That means the magnetic field cannot hold it. It flies straight out of the plasma and passes through the magnetic cage. This may sound like a problem, but it is actually part of the design. The escaping neutron carries most of the reaction energy away from the core, and the reactor is built to capture that energy in the surrounding structure. Surrounding the plasma chamber is a special layer often called the blanket. In many designs, this blanket contains lithium. When fast neutrons from the fusion reaction slam into the blanket, their kinetic energy is absorbed and converted into heat. The lithium also plays another important role. It can help produce more tritium fuel, which is needed to keep the reaction cycle going. But from the point of view of electricity generation, the main point is heat. Fusion does not usually send electricity directly into wires. Instead, the reactor first turns nuclear energy into thermal energy. Coolant channels carry that heat away from the blanket, protecting the machine and moving useful energy to the next stage. In other words, the plasma creates energetic particles, the neutrons escape, the blanket absorbs them, and the coolant becomes the bridge between the fusion core and the power plant. Once the coolant carries heat away from the reactor blanket, the system begins to look more familiar. The hot coolant transfers energy into a heat exchanger where water is turned into high-pressure steam. That steam rushes through turbine blades, forcing them to spin at high speed. The spinning turbine drives a generator, and inside that generator, motion becomes electricity through electromagnetic induction. Magnets and coils interact, producing an electric current that can be conditioned and delivered to the grid. So, even though the fusion reaction itself is incredibly advanced, the final electricity step is based on a proven principle used across many power plants today. The difference is the heat source. Instead of burning coal, oil, or gas, a fusion plant aims to use star-like reactions with very low carbon emissions, abundant fuel sources, and no long-lived chain reaction that can run away, like in conventional fission reactors. So here is the full journey. Fusion begins by heating deuterium and tritium until they become plasma. Magnetic fields hold that plasma away from the reactor walls, giving the nuclei a chance to collide and fuse. Each successful reaction creates helium and releases an energetic neutron. Because that neutron is uncharged, it escapes the magnetic field and enters the surrounding blanket. There, its energy becomes heat. Coolant collects that heat. A heat exchanger makes steam. The steam spins a turbine, and the turbine drives a generator that produces electricity. That is how a plasma reactor can turn the physics of stars into power for the grid. If you enjoy clear explanations of advanced energy technology, make sure to subscribe, like, and share this video. The future of power is being built step by step, and you will want to keep watching. For more information, visit www.globalpowernews.com. My YouTube channel is Nawaz Lakho Power Pro. Do not forget to subscribe, like, and share. For more than a century, almost every big power plant has shared the same basic trick: make heat, boil water, spin a turbine, and generate electricity. It works, but it is bulky, mechanical, and limited by the physics of steam. Now imagine a future reactor where the hottest, fastest particles do not wait around to boil water. Instead, we catch their motion directly as electricity. The contrast is dramatic. A conventional steam turbine is a masterpiece of engineering, but it is also a chain of conversions: heat to steam, steam to rotation, rotation to current. Direct plasma generation tries to shorten that chain. In a fusion like plasma, particles already carry enormous kinetic energy and electric charge. The question is whether we can collect that energy before it becomes ordinary heat. This is not a claim that commercial fusion plants are about to throw away turbines tomorrow. Today, most practical designs still expect a thermal blanket, coolant loops, and turbines. But direct conversion is one of the most fascinating future-facing ideas in energy technology because it asks a radical question. If plasma is already charged and moving, why turn all of that organized motion into heat first? The first approach is the electrostatic converter. Picture high-energy ions escaping from magnetic confinement and flying into a stack of charged grid plates. Those plates create an electric field pointed against the ions' motion. As the ions climb that electrical hill, they slow down. Their kinetic energy does not disappear. It is transferred into electrical potential, producing high voltage direct current. In the ideal version, this is like regenerative braking for fusion particles. Instead of dumping all their energy into a hot wall, the converter decelerates them in a controlled electric field. That means fewer heat exchangers, less boiling water, and fewer rotating components. The challenge is brutal precision. The particles have different energies, directions, and charges, and the grids must survive an extreme radiation environment. A second route treats plasma less like individual particles and more like a flowing, electrically conductive fluid. This is magnetohydrodynamic generation, usually shortened to MHD. The name sounds intimidating, but the core idea is simple. Push a conductive plasma through a strong magnetic field, and the moving charges inside it can be separated and collected as electrical power. Inside an MID generator, superheated plasma blasts down a linear channel wrapped in powerful magnets. As charged particles move through the magnetic field, the Lorentz force nudges positive and negative charges in opposite directions. Electrodes on the channel walls collect that separation as voltage. There is no spinning rotor in the plasma stream. just magnetic fields, electrodes, and a violent flow of charged matter. That absence of moving parts is why MHD looks so elegant on paper. A hot conductive flow becomes a kind of fluid dynamo, turning motion directly into electricity. But again, the engineering is severe. The channel walls face heat, erosion, radiation, and electrical stress all at once. For fusion systems, designers would also need to control impurities, plasma stability, and efficient coupling to the rest of the plant. So, why chase this at all? Efficiency. A traditional steam cycle in a real power plant often lands around 40% efficiency, depending on temperatures and design. Direct plasma capture is attractive because some theoretical concepts aim far higher, sometimes around 80% or more for the directly captured particle energy. That number is not a guaranteed plant efficiency, but it shows the scale of the prize. The most realistic future may not be one magic device. It could be a layered system. Electrostatic converters harvest energy from charged fusion products. An MHD stage extracts power from conductive plasma flow. A surrounding blanket captures neutrons and leftover heat, producing additional power through more conventional methods. In that hybrid picture, every pathway is trying to waste less of the reactor's original particle energy. The important takeaway is not that steam is dead today. It is that the next energy revolution may come from questioning the old conversion chain. If fusion and advanced plasma systems mature, direct electricity generation could make reactors simpler, faster to respond, and potentially much more efficient. The science is real, the potential is huge, and the remaining engineering is exactly the kind of frontier that defines a technological age. If you enjoyed this look at plasma power, hit like, subscribe, and tell me in the comments which idea sounds more promising to you. Electrostatic conversion, MHD generation, or a hybrid reactor that uses both. The future of energy may not just be about making hotter machines. It may be about learning to catch motion, charge, and light before they fade